Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this video we see how we use the pH scale to distinguish between acidic, neutral and basic solutions, and then go on to carry out some simple pH calculations involving acidic solutions.
For the benefit of the small number of people that were away when we started this section, then we'll do a quick recap. If we look at something like this is ethanoic acid. Okay, it's one you possibly won't have come across before, but I'll just quickly write out the equation. You don't need to write anything. This is just a review that will cover everything we have done in the last double period. So the first thing is we started off by saying that acids are, from last year, we looked at last year's knowledge, acids are things that when you added them to water released H+. Well, we have to sweep aside that over simplification, in that H+ is basically a proton. It's just hydrogen with the electron removed, so it's just a proton, and protons on their own are not stable. And because we carry these reactions out in water, that proton will latch itself straight onto the nearest molecule, which is generally water. So you form this ion, the hydronium ion, okay, H3O+. And overall, if we look at this reaction then, this is ethanoic acid. If you see something, as an aside here, you'll do organic chemistry later this year, if you see hydrogen attached to carbon, it does not come off. Okay, a carbon-hydrogen bond is one of the strongest covalent bonds there is, so it does not break easily. However, the OH bond here does. And so what we're doing is we are literally taking H+ off that acid and sticking it onto the water. So what we say is that the ethanoic acid donates H+ to water, and it forms this ethanoate anion. And that's how we define an acid. An acid is a proton or H+ donor. By inference, if we look at H2O itself, it accepts H+. And a proton acceptor is what we define as a base. So everything's changed from last year. Okay? We're going to be dealing in terms of H3O+, not H+. And we're actually redefining. It's not something that releases H+, it's something that donates H+ to another molecule. And that's really important. Okay? And similarly, this is a little confusing for those who haven't seen it before, but if we were to take NH3, which is a standard base from last year, and we add water to that, again we get this reversible reaction, and we get NH4 plus OH minus. And this time, okay, the H+ goes in the opposite direction. It's from water to ammonia. Ammonia accepts H+. So that's what makes it a base. Okay? So we're talking in terms of definitions that involve a sort of a mechanical process, something being moved from one thing to another. So an acid, you're losing H+ and you transfer it to something else. In the case of a base, the H+ is coming in the opposite direction, and the base is a proton acceptor. So acid, proton donor, base, proton acceptor. And we went on and we saw that if these are both reversible reactions, in these cases, what's actually happening is this species, the ethanoate ion, reacts with H3O+ to form the reactants again. Then what it's actually doing is this is actually accepting a proton back. Okay, so you notice how it's the base bit, you see, it's got blue. I've got to have blue, so I'm really sad that way. So the blue telling you that H+ is going back. Well, it's accepting a proton. That means that this is a base. This is an acid because it's donated a proton. Okay. In this case, we've got a base. And here, this accepts or donates a proton across. So this is acting like an acid. It adds, or it donates H+ to OH minus, so this makes it an acid. And what we call these two substances here are the conjugates. So this is the acid, and this is the conjugate base of that acid. So a conjugate base of an acid is the acid with H plus removed from it. Okay, in this case, we've got the base ammonia, and this is the conjugate acid. The conjugate acid is the base with H plus added onto it. Simple as that. Okay, and then it got really nasty, because if you look at this a bit more carefully, this is accepting a proton. So this makes this a base. And of course we've not thought of water being a base before, have we? And so this is donating a proton. This is an acid. Okay? So if we look at water, that's the base. This is the conjugate acid of the base water. And similarly, if this is a donor, this is an acid. And so this is the conjugate base of water. Okay? And so what you end up with are two pairs. This base with its conjugate acid, and this acid with its conjugate base. Okay, so all of these types of reactions consist of a conjugate acid base, or a pair of conjugate acid base pairs, if you sort of think. Okay? And then we finished off by making a clear distinction by what we mean by an acid or a base and an acidic and basic solution. So an acid or a base is something that either donates, in the case of an acid, or accepts, in the case of a base, a proton. So it's the thing, the actual noun, the thing that actually gives or takes. When we come to look at what we mean by an acidic and basic solution, we need to look at what's formed, because it's about the solution itself. So something that's formed in that initial reaction is making the solution acidic or basic. And in the case of an acidic solution, it's because this is being formed, H3O+, which is called hydronium. The fact it's being formed as part of this reaction means that this unbalances the concentration of OH3O+ and OH-, and that's something we're going to move on to because there's an equilibrium involved, so it's a little bit more subtle than was explained last year, and we'll look at that in a short while. In the case of this solution is basic because OH- is being formed, and that alters the concentration of OH- in solution, and that's what makes it basic. So these are the things that make it acidic and basic. This is the acid, and this is the base. So that was basically last lesson, double lesson. So you've got that in about 5 minutes. Hopefully that hasn't confused everything. Before we can go on to look at this and this, as to why this makes the solution acidic and why this makes the solution basic, we need to look at how we measure it. And then we look at the consequence of that afterwards. And you already know how we measure acidity. We covered it last year at level 1. We use the pH scale. And so I want to look at that this lesson. How does it work? And we're going to do some very simple calculations involving it. Okay? For many of you, most of you, you probably won't have come across a logarithmic function before. Okay? So we're going to practice that. Now, for the next lesson, also, you need to make sure you bring your calculator. If you've got your calculator, now is the time to get it out. Okay? Because you're going to need to use that logarithmic function. Okay? Now, the thing about the pH is it's a measure of, sorry, there's a mistake, I put the plus in there. It's a measure of the concentration of hydronium ions in solution. Okay? So, and this can range from enormous in a concentrated solution to tiny, tiny, tiny in something like a base. And we'll get to how there can possibly be H3O+ in a base in a while. Okay? Now, the thing about a logarithmic function is you can calculate the pH of something if you know what the concentration of H3O+ is. What about if you know what the pH is, how do you work out H3O plus concentration? It's not, you can't rearrange it, it's a reverse operation. So you do what we call take a reverse logarithm. Only there's no log in it, okay? Really, it's an anti-log, but we don't call that anymore. So if you want to calculate the pH, and you know the concentration of H3O plus, then you can do that straight forward. Okay, shall we do an example? So we'll keep it completely generic. Say we know what the concentration of H3O plus is. We won't even say which acid it is. It's just 0.105 mole per litre. Let's write it out. pH is equal to minus the log of H3O plus, which is equal to minus the log of 0.105. So,
yeah, I put negative log.
If you put negative log and it works.
okay, this would be a concentration, a fairly typical concentration of an acid. So if you go and look at the bottles we've got in the back room there, they'll be about 0.1 mole per litre concentration. Now what I would recommend is, with these things, to actually round it to 1 decimal place. Because it's a logarithmic scale that goes and it's going between 0 and 14, okay, it's probably, you'll avoid any sort of confusion by just basically rounding it to 1 decimal place. So that's 1.0. Okay, so you're 1 on the scale. So 1 on the pH scale means it's a typical acid. If you look at something that's a base, on the other hand, no, it's a typically, that's just any sort of acid. That would be, yeah, it would be a strong acid, but don't let that worry. It's a fairly dilute acid. Okay, so it's fairly dilute, a typical dilute, say, HCl solution. Yeah, that would be its pH. Okay, now. Now, this is something you've got to get used to. Okay, small numbers in chemistry can be very small, and that is very, very small. But we tend to represent them using scientific form. So try to use sort of normal form, if you like this, when it's fairly close to 1. But if it's getting very, very small, you must use scientific form. So for the benefit of those that may not have used their calculator to do things like that, 3.06 EXP is the best button to press, minus 12. Yeah? So you want to do minus the log, so pH is equal to minus the log of H3O plus, which is equal to minus the log of 3.06 times 10 to the minus 12. Okay? Can somebody do that? So you type that in, minus log, bracket, 3.06 exp minus 12. 11.5. And that's the pH you would associate with a base. Now that number there and that number there cover an absolutely huge range. This one here is 11 orders of magnitude smaller than that one. And that's why we're using a logarithmic scale. Is it changes these somewhat hard to handle numbers into something that's usable. Okay? That's the reason we're doing it. Okay? It's just much easier to get a handle on what we're dealing with. Of course, the next thing we need to know is how does these relate to actual acids and bases? How do we know these concentrations? And that's what we're going to move on to next. But I want to spend a little bit of time going through the logarithmic scale, okay, and how it works. Because logs cover all sorts of, there's different types of logs. Yeah. These are based on 10, so it makes them easy. And how does that come in? Well, remember I said you can't rearrange this that has its reverse operation. So, if you know what the pH is, how do you calculate the concentration of H3O+? Because we need to know that sometimes, yeah? So you measure the pH. So you pour in your acid into a beaker and you put your pH meter in. And so, let's have a look at the reverse operation. Okay, so those are the two biggies today. Now you don't necessarily need to remember these because you're given them now. From last year was the first year, you get both of these on a supplementary data sheet. So that's the reverse, like I say. So there you go. See if you can do that. Okay, so the concentration of H3O plus is equal to 10 to the minus 5.5. Now we're going to write that in standard form. 5. 3.5 did you say?
5.
5 point anything? And you need to put the units in, which won't mean anything. And also do it to 2 places here, because what we're doing...
3.16.
Okay. Okay. Now, what I've done is I've quoted this to 3 significant figures, which won't mean anything to you, and I've also given the units. Just copy it down for the moment. You'll understand about significant figures and the actual units when we've done quantitative. Okay, so write it like this. This is, as you know, called scientific form, and it's because these are what we call base 10 logarithms. That's why you write it log. That's why it's times 10 to the minus something. Okay. Now, to give you a feel of what the pH scale is about, if we write out the pH value, you can do this as a little table, and then put the concentration of H3O plus in the next column. And I want you to do pH of 0. I want you to calculate this. So you're going to use this expression. You're going to do, so we say 2, 7, 9, and 14. Okay, so we're spreading that along the scale. So this is very acidic. Should we say 3 there? Let's put 3. This is fairly mildly acidic. Then you've got neutral, mildly basic, and very basic. And you'll see what I mean about how a logarithm compresses the scale to a manageable size. Is that what you got? I don't know. You're supposed to be using this equation with these values. So 10 to the power of 0 is always, anything to the power of 0 is always 1. I'll give you that one. But what you're doing is putting 10 to the minus 3. 1 times 10 to the minus 3. 10 to the minus 7. 1 times 10 to the minus 7. So what you can see is you've got these nice little numbers here replacing these. Okay, and that's why we're doing it. So the pH scale is telling you that the concentration of hydronium ions, if you take it from 0 to 14, goes from 1 mole per litre to 1 times 10 to the minus 14 moles per litre. However, that, even though it's as tiny as that, is significant. And it's significant because we can measure it. If we can measure it, then that's why we can give a pH of 14. So I think this is quite instructive because it tells you why we're using the log function. Which would you rather have, these or these? Nice round numbers, yes?